All right, howdy, what's going on? So, I'd like to talk a little bit about this effect. It's not enough to get there. We're going to have to talk about some other things before we can completely explain it. Do a little bit of the explanation of why this doesn't quite work in the example. But actually, this does work. What doesn't work is the amount of knowledge we have about fields, right? So right now we don't have a lot of knowledge about fields. So we don't want to get too big into that. So you might remember that if we had a cylinder and we rubbed it with sheep's wool, it would get charged up. So let's give it a positive charge. So the sheep's wool would, I guess, steal some of the electrons. I hope that's right. It doesn't matter too much for the example, except I'd have to put the rod at the bottom instead of the top. So what happens there? Well, if you had some paper or something like that sitting around, you have some like little pieces of confetti, and you brought this guy next to it, the confetti would sort of drift up onto the rod, even though the confetti is not charged. It would be attracted to the rod, right? So that's weird. Even weirder is if you had some, little flakes of gold, let's say, sitting over here. You have little gold flakes. They would also sort of drift up to the rod. So we've got an insulator and a conductor, two different things, and they're both attracted to this rod that's charged even though they're not charged. They themselves aren't charged. Weird, right? So somehow they feel a force. Part of that is going to be due to the inhomogeneity of the field, but I'm just going to talk about the homogeneous field right now. The nice uniform field, the non-uniformity of the field. It's still homogeneous, I guess. So what happens there? Well, let's look at the gold first, right? The gold, let's pretend it's a spherical flake of gold. We put it in an electric field like the one we just talked about in part 1. That's coming up towards the rod. Now let's pretend you're an electron, right? If you're an electron and you're right here, right, you're going to be pushed away from that. So the free electrons will be pushed sort of down towards the edge, right? And that means that in this neutral piece of gold, there's going to have to be positive charges where all those negative charges came from, right? So the total amount of charge has to be sort of the same, right? The total amount of charge has to be 0, right? So there has to be the same amount of positive charge and the same amount of negative charge in there. So the positive charge accumulates up there. Negative charge accumulates down here, at least the negative charges that can actually move, right? It's only the moving charges in the conductor and the metal that can do that. In the insulator, the charges don't move, so something else happens. And so because of that, we end up with a little thing here that we call the polarization. So that metal flake becomes polarized, and that will allow a non-uniform electric field to pull it up, but only a non-uniform electric field. I'll show that for a uniform electric field it does not work in the example. Later on we'll talk about non-uniform fields, and maybe I'll give you an example of a non-uniform field pulling something up, okay? But right now we just care about the basics, right? Which is stuff like calculating the polarization. Okay, so what happens then in a piece of an insulator, right? We've got our piece of paper there. It's going to be a spherical piece of paper, a spherical flake of paper, because I know those happen, right? They don't happen, but life is easy with those spheres. Well, in that case, the electrons can't move around. An insulator like paper or rubber or something like that, the charges don't move around, they stay put. But what does happen? Well, at the atomic level, you have this nucleus that's positively charged, and it's really heavy. It's, 2,000, 4,000 times, 4,000 probably, times heavier than the electrons. And then you have your electrons that in the field will get pulled down like this, so that the center between those two spots is different, right? So before the field, right, the electron cloud is symmetric around the nucleus, more or less. But then when it gets put in the field, it's going this way, right? The electric field is going up this way. The nucleus gets pulled up, but it's kind of slow because it's big, and the electron gets pushed down, right? And so you end up with sort of this oval charge and a little bit of a polarization at the atomic level, right? So you have an atomic polarization here. So we have a little polarization pi there. Not 3.14, just pi. So that guy has its own polarization. Each atom in the paper is going to polarize. Just a little bit. Just a little bit it's going to polarize. So that's what's going to happen here, is for each atom inside of this guy, you're going to have the negative charges kind of get pulled down at that level. But what that means is that basically everything's, packed in tight. So not that tight, but just a lot of empty space in there. But that means basically that there's no net charge in the center, but there's nothing, because you pull the negative charge down and the positive charge from the next one is up here, right? So you can have some sort of compensation everywhere except at the edges, right? So you have a net positive charge on top and a net negative charge on the bottom, and you end up again with a polarization. All right, so we have two situations, both of which give you a polarization for different physical reasons, all right, for different physics. That's more or less all there is to it. So that's what we're doing for 3. When an object is put in an electric field, when an uncharged object is put in an electric field, becomes polarized. Okay, and basically what that means is you end up with a polarization P, which is going to be equal to the charge accumulated at the top, Q, this guy, times the distance from the top to the bottom in the direction of the electric field. That's the direction of the electric field. That's the distance from top to bottom. That's the charge at the top. Maybe I should say the uncompensated charge. No, I'll just say charge at the top. The uncompensated charge at the top. Q bottom is equal to minus Q top equal to minus Q. Okay, so this charge and that charge, because of where the charge is coming from, have to be the same. Now, what I mean by uncompensated is that you could have a charged object that you put in the electric field and the same thing happens, right? So there's going to be two components. One will be the excess charge plus the polarization that comes from the compensated charges. So we won't have to worry too much about that. We can also write the polarization for the insulator, an insulator only for this guy, here, as equal to the atomic polarizability times the number of atoms times the electric field. Okay, where E is the electric field, right, which is a vector at every particular point in space, and that's equal to the magnitude of the electric field times the direction of the electric field. Okay. So how do you get rid of this E hat? You just ignore it, and you get rid of the little arrow. That's all. Okay, so that is basically what happens inside the material because of the things we've been talking about at the beginning. And that's what allows the basics, the basic thing that made people think there was something special about electricity to happen in the first place. All right? Okay, well, thank you very much. It's been a pleasure talking to you. Why don't you come in next week where we'll talk about how fields get there in the first place. So now we've talked about charge, and we've talked about what happens to a charged object when it's put in a field. Next we're going to talk about how we get those fields, what generates those fields, and stuff in that region. All right? Talk to you later. Bye now.